Hello, and welcome to this fourth screencast, this time on dyscalculia. The reason I wanted to study dyscalculia was because I knew of it, but I didn't know that much about it. I found this paragraph on an 8-year-old girl, Claire, to be particularly captivating. Claire demonstrated normal skills for a grade 2 student in that her motivation was strong and intention was strong. However, she particularly struggled in math. She had trouble with her number skills. She found that she had difficulty with place values, so like tens, hundreds, and thousands. And in particular, when it came to adding and subtracting, she was using a very painful method of counting on her fingers. One of the leaders in the field of this research, Brian Butterworth, finds it difficult to study the problem of dyscalculia. That is in particular because there are so many reasons for being poor at math, which can stem from inappropriate teaching, student behavior problems, missing lessons due to illness, or the anxiety that is often associated with mathematics. Further, many are less than willing to be sympathetic when people struggle with mathematics, and in particular the assumption is that either the person is lazy or maybe just a little bit dumb. Also, math deficits can sometimes be linked to literacy difficulties, and usually the literacy difficulties get treated first. Finally, math is a difficult subject to learn, even in the early grades. It requires an understanding of a variety of skills, like counting, estimating, as well as being able to retrieve arithmetic facts. On top of that, knowing laws, as well as procedures. Is it multiplication before division? Is it addition before subtraction? Oh my goodness, I got that all mixed up. And there are many rules. So there's lots of problems when coming to study this topic. It's difficult to precisely define what dyscalculia is, but it is as prevalent as dyslexia and affects about 5 to 7% of the population. However, it is definitely not as well known. The only way this syndrome is screened is by noting poor achievement on standardized tests. Using standardized tests, the following mathematical deficits have been noted: a severe disability in learning arithmetic, and an inability to understand the properties of how or when or what to manipulate with numbers. There is a delay in aspects of counting, and in particular students don't count in the correct order, 1, 2, 5, 7, 8, or sometimes double count 1, 2, 2, 3, 4, 4, 5. They also have a delay in counting strategies for simple addition. So for example, they will count all, meaning if they were to add, say, 3 and 5, they will go 1, 2, 3, 4, 5, 6, 7, 8, instead of counting on, which means that they start at 5 and add 3, so 5, 6, 7, 8. They are also known to have what's called finger agnosia, and what that means is they're unable to make connections between counting on the fingers and the operations required. And that's what was meant earlier with that painful counting on fingers. They don't understand the magnitude of numbers, and so comparisons are not possible. And they don't know the distances between numbers. So for example, a lot of studies are done looking at distances, say, between 7 and 9. And dyscalculics would think that a distance between 1 and 9 is the same as the distance between 7 and 9. There is more information at the link on the bottom, and I've also put it into the references. It gives basically an itemized table of what to look for in the classroom. In order to understand the pathophysiology, we first need to know what the physiology of the brain is that is required to understand mathematical processing. In particular, most of the studies have demonstrated that a lot of number processing goes on in the horizontal segment of the bilateral intraparietal sulcus. So functions like number processing, number detection and comparison, number comparison task sets. So when I talked to you earlier about measured numerical differences, tasks that emphasize quantity, all of these seem to be an issue, or all of these seem to stem through the horizontal intraparietal sulcus. And just so you know where in the brain we're talking about, the interparietal sulcus is in the parietal lobe. I've indicated it here with the red. A lot of the research talks about some terms in mathematics that we should know about. So there are different ways to represent numbers. There is symbolic, like the fraction 2/5, and there are non-symbolic ways to represent numbers, like by using this picture and shading 2/5. So the current theory is that there is a single core deficit, numerosity, that characterizes dyscalculia. And numerosity is fundamental to the development of arithmetic skills. So there's a deficit in number or non-symbolic representation of numbers, and that's why children have difficulty understanding the quantity or the size of numbers. This is caused by a structural or functional impairment in the HIPS, HIPS. And as we've talked about, I said on the slide before, this gives a difficulty for children or even adults to understand the size of numbers. In dyscalculic children, activity in the interparietal sulcus is reduced when carrying out number comparisons and arithmetic. This may indicate that this area of the brain is not being used. Further, the IPS is not developed to the same extent as in other learners, and there is reduced gray matter in this region in dyscalculics. Finally, there are differences in connectivity between parietal regions and the occipitotemporal regions known to be associated with number processing. How can dyscalculia be recognized? From the Wilson and Dehane chapter in the Butterworth and Kovacs 2008 paper, it is noted that dyscalculia can be related to a severe disability in learning arithmetic, the branch of mathematics that deals with both the properties and manipulations of numbers. Over their education span, children with dyscalculia fall well behind their peers in mathematics. Further studies have demonstrated that dyscalculia will persist into high school, with young people being highly amotivated to learn mathematics. Adults suffering from this disease are more likely to earn less money, yet spend more. Further, they are less productive, more often ill, or in trouble with the law. They generally need more help at school, or may be more likely to drop out. As there are few preventative measures available and only limited longitudinal studies, the effect of early intervention is unknown. So, what can the educator do? The first step is to recognize that there is a problem and to reassure the child and the parents that something can be done. Early intervention looks at giving dyscalculic children more individual support and diagnosing the child's gaps in understanding. Butterworth and Kovacs feel that rather than trying to fill the conceptual gaps, the neuroscience suggests that remediation to build the foundational concepts should come first. In particular, special focus should be placed on the meaningfulness of numbers. There has been some success in using concrete manipulative activities, in particular those that give meaning and sense to the magnitude of a number. Rather than drilling math facts, more time spent on comparing numbers with tangible ideas of size can be more useful. In particular, they emphasize an information feedback strategy. The loop is between the learner's goal, their action, and some information feedback, which results in a new goal. Butterworth and Kovacs maintain that this information feedback provides intrinsic motivation in a task, giving it greater value. For example, special education teachers can use physical manipulatives like Cuisenaire rods, see the picture, to help students determine which combinations of numbers add up to 10. So for example, if they take 2 green bars, then that will add up to 10, whereas if they take a blue bar and a purple bar, then that will add up to 10, and so on. It's these type of activities where they're giving an understanding of size that helps them to understand. The authors recognize that having specialized teachers to work with individual students is costly, and so have developed adaptive software based on their neuroscience findings. In order to stimulate the IPS, most of these games are using dot arrays to show the size of numbers rather than just the symbol. They are currently testing a number bonds game which works in a similar way to the Cuisenaire rods to help students determine the size of a number. The advantage of having such adaptive software is that a student can work on this active manipulation independently, receive personalized feedback, and develop their own goals. This type of adaptive learning is similar to that found in intrinsic learning, and the hope is that dyscalculic students will benefit from its application. It is too early to tell yet. Again, the references have been attached. and they will also be found on the last page of the Google Doc. Thank you very much for listening, and I hope you've enjoyed these 4 presentations.